This is about a project I did over Christmas, New Year's, and it's sort of a sort of restrained end of. It's a sort of a strange little topic area, but so I feel like I need to explain how I backed myself into wanting to try doing this particular thing. But yeah, it's basically sort of following on if people saw my last presentation, which was talking about looking a little bit at bytecode and how that works, and we were looking at Lisp for Erlang and some of these other things and how they all turned down into bytecode and how it was all looking at registers and opcodes and things like that and how things were represented inside the Beam virtual machine. So this is sort of a follow-on from that, but with a particular application. So let's start off with the universe, just set the context a bit. So I've been mucking around with Unity, which is a game development platform with C# as the language, just for, I was doing a sort of aeronautical simulations for a wind power thing that I was looking at. And the way that things work and in Unity, and I think it's pretty common in a lot of game development platforms, is you have game objects, people or ships or weapons or objects that you pick up in an old abandoned lighthouse or whatever. And the general structure that people do, it's very OO, but the idea is you attach behaviors onto these objects. And so the idea is, and that's the idea is to make things extensible. Like you can go and get, in my case, you can go and get some blocky sort of object, like a box, and then you can say, actually that's an airfoil. It's got the properties of a wing, and then all of a sudden you can tell it about the airfoil and what its lift is and all that sort of stuff, and then you can start simulating this box flying around as if it's a wing on an aeroplane or a windmill, and So I was mucking around with that, and then I was also reading a fair bit of Neil Stephenson's new novels where he's talking about simulating new universes and people sort of like going into universes, and it started making me think about massively multiplayer game simulations and how awesome Elixir and the Erlang virtual machine would be for this sort of stuff. And so I started, and thinking about agents in Elixir and Erlang is not new, but I was just thinking, I wonder how I'd implement this. And I sort of managed to start toying around with it till I got down to the point where I was thinking like, if you had a really big, complicated game universe or robot wars or something like that we all wanted to set up and simulate, it'd be nice if people could contribute behaviors. And then I was sort of thinking, well, how could people contribute behaviors? And just where my head was at the time, I started thinking about being able to contribute them as compiled code so that you could actually have a market for behaviors, and people could, so people could sort of, it wouldn't be open source, which I know is a little bit evil, but it's just where my head was at the time, looking out at the beach at Mollymook. I don't know why I have that reaction to beaches, but there you go. So if we look at, these little modules, like on the Erlang platform, these would be Beam files, and the idea, I'd sort of like want to have these modules sort of plug in, and they'd have access to sort of an API that would let them access the things that they were allowed to access, and they weren't allowed to just like jump over and take someone else's food or just run roughshod all over the universe. They have to, they have to be constrained. So looking at one of these modules, what you sort of want to be able to do is you want to be able to sandbox, and you don't want them to be able to just go out and do anything. Like you don't want them to go and be able to go and crawl up and down the stack and see what the variables were in the code that called them. And you don't want them to be able to go and use I/O, or just to be able to send and receive messages or make system calls or all these sorts of things. You want to basically give them a whitelist of modules that they're allowed to talk to. And those, I think you can see my cursor, yeah. Because it's just screen share, right? So the idea is that you'd be able to whitelist some modules, and they could go over and call other things for you, but you could not call those other things directly. And remember that this code could have come from any language. Like this could be Erlang. This module, once things go down to module level, Erlang or Lisp for Erlang or all these things, they're all basically the same or very, very, very similar at the module level. So these could have come from any source code. They've all gone down into a Beam bytecode, and we want to be able to sandbox them or control them, or look at them before we load them and say, are you doing anything naughty, or just basically restrict their vocabulary to a subset. And I will point out, there are much less crazy ways of doing this. There's Robert Verding also did a Lua, L-U-A, a Lua interpreter for Erlang, and the safety you get there is you're writing in a completely different language, and so you can't just go and reach out to anything. It has to you have to explicitly expose particular APIs to Lua to be able to do that. And Lua is actually used a lot for plugin development in games, like particularly I know in Xplane, for example, a lot of the extensions for Xplane and stuff are written in Lua. So that would be a reasonable way to do it, but I just got a thing in my head about this would be fun. By the way, if you think that Erlang process info looks a little bit like a COVID-19 microbe, then it is. You'll see it comes back. It makes many appearances in this presentation. Okay, so next we need to express those. What we want it to be able to do. I need to have a test. I need to be able to have a test of what I want code to not be able to do. And so I had this little test thing that we did. Basically, imagine that Bounty 1 module is one of these plugins. At the moment, it just returns -1. It's going to guess a number. But then in our test, we're going to use crypto to generate a random number. And then we're going to use this safeish library that we're going to write and load a file. And what should happen... this test should fail. When this test passes, it means that someone has broken the sandbox that we put our module in. Okay, that's But for people who don't know, so this is a binary pattern, and basically, strong round bytes generate 16 bytes, and we're saying here is a 128-bit integer and called secret, and so now secret's equal to this big random 128-bit integer. And then this little marker here says, this is a match for people who aren't used to Erlang. This is actually hang on. Well, we're just basically saying, rather than normally in Elixir, this would assign the value of this thing, secret would get assigned to that. But because we put the little anchory thing there, that's basically saying we're going to, this pattern is going to fail to match if Bounty 1 guess doesn't match the value that's already inside secret. Okay, so that's this is an example of what we don't want to happen. And so if somebody wants to break this, all they have to do is work out some way to reach into the call stack and find out what that secret number is. Okay, so then the next thing you need to do is you have to make up your shopping list of what are the things that you want these little modules to still be able to do? And rather than having a blacklist of things you can't do, because you never know what things might be added in the next version of Erlang, Elixir, or whatever, you actually need to go through the slightly laborious process of whitelisting the things you think are safe. Notice think is a key word there. And so I actually had an opportunity on my holiday to read all of the library documentation for Erlang and Elixir, and just basically make a list of the things that I thought were safe. And so I've just made these great big lookup map sets and lists either of entire modules which I thought were safe to use, or if there were some naughty things in the modules, you had to make a list inside the module, like in the case of you had to actually list the particular things that you wanted people to be able to use inside a module. And so, and the thing is, you have to still make it permissive enough for this thing to be useful. Otherwise, you could make it super secure by basically whitelisting, the addition symbol or something like that, and then you'd have a little language that you could add numbers with, and that would be it. So it has to be as permissive as possible, but just block out the things which are not, which could cause problems. So the sort of things that we don't want people. So some of the interesting things that come up here are we don't want people to be able to construct terms or atoms at runtime, because that would allow you to, say, construct a function literal and go and call a function that at compile time. We're doing all of this at compile or load time as we're loading the module. We have to be able to see what functions it's going to call. And if you let people assemble their own Erlang terms or assemble new atoms from strings, then they could potentially construct a call which would break your sandbox. So there are some things that you have to leave out, like dynamic construction of atoms. So we couldn't allow string to atom or string to existing atom, because these things would allow people to construct calls to things that weren't there when we looked at the code that we were loading. The other thing is, sometimes it's not black and white. There are some edge cases about, what are we assuming that this thing is allowed to do? Like, for instance, there's a thing, there's a process, Erlang has a process dictionary, which is basically just a big map that belongs to the process. Follow-up question of that is, did you actually know there was such a thing as a process dictionary? It seems very unpure for the functional programming types. To basically a nice big global variable scope where you can dump stuff for your process. But then the question, so you have questions like that, like, do we expose that to this thing? Is this thing supposed to be able to share things with the rest of the process that it's being run in, for example? And I don't know the answer to that. Okay, so next, just going back to my last presentation, we've got our whitelist. Now we need to look at the Beam file and work out, well, is the Beam file breaking any of these? Is the Beam file sticking to these whitelists, or is it doing things which aren't on my whitelists? So that means we're going to have to look at the Beam file format. So back to the very cool book that I talked about in my last presentation, the Beam book, which was originally going to be an O'Reilly book, but didn't actually get all the way through publication. So it's been open sourced, and I'm happy. I only know the name of the company. I'm afraid I don't actually know his name, but the guy who was the author is sort of maintaining it as an open source project, and it's really good. And I just putting a plug in for it. If we all love this platform, we should really support the people who are documenting the actual virtual machine, because it's a really sort of existentially fundamental thing to know about. If you're going to live in this virtual machine for a lot of your working life, you should know a bit about how it works. If for nothing else than to stop some of the sillier arguments that happen about what language is what, because at the end of the day, it all turns into bytecode. So the Beam file format. Just one interesting thing I noticed about this here is that it's the file format was based on this thing called EAIFF, and EA is actually Electronic Arts, and this format, EAIFF, was actually designed for Commodore games in 1985. So it was like a standard to share like music and audio and artwork in games. So you can actually truly say that some fundamental parts of the Beam, of the Erlang technology, are actually game technology. So I feel like it's coming full loop from Unity and stuff. Like Marble Madness is actually was an EA Arts game that came out around the same time as Erlang was being developed. So you can actually think of, it's nice to see some little historical things that happen. So just remember, when you're programming on the Beam, it's a game in a way. Okay, but then what that basically tells us about the Beam file format and this EAIFF format is it's just basically the idea that you have a file, it's got a header, and then a series of chunks, and the chunks have labels on them, and I suppose for EA it would have contained music or things like that. But in the case of the Beam file format, there are a few chunks of data, things like lists of atoms that are used, lists of working from the top. That's a list of atoms. Then you've got lists of literals, lists of imported functions, lists of strings, lists of functions, list of exported functions. They all wind up in these chunks. And you also have abstract code and code. And so, very chunky. Chunk is just like one of those pleasant words to say, chunk. So chunky, you can load it. That's a reference to an Australian dog food commercial from the 1980s. Just keeping with the 1980s. But the really cool thing here was like, the lazy programmer in me said, abstract code, we know about that, because that's what I was talking about in my last presentation. So here's a little fragment of code. that shows you how to get at the abstract code if it's embedded in a Beam file. You can just basically load up your file, binary, read in all the bytes from the file, and then use Beamlib, which is an Elixir Erlang library, and you can actually say, here's my bytecode, and you request a list of chunks that you want to extract from the Beam. And that gives you, I've just given a fragment there, but if you remember my test function that was just like a function called guess that returned -1, then this is the sort of stuff that's an extract of what abstract code gives you. And I thought, this is cool. This is actually, I think in the Beam, it's stored as, Erlang has term to binary and binary to term, which is probably what Ertz and Amnesia and stuff use for storage. When they're serializing, you can just basically serialize bits of Erlang Elixir expressions into bytes. And so what this does, I think abstract code is actually been term to binaried. And what this does for you is it binaries to term and just gives you back these nice, tuples and lists and atoms and integers and things, which makes it really easy to look at. Although interestingly, to represent a -1, it's actually put in, I found that this is a bit strange. It's actually represented that as a positive integer 1 or 0 minus 1. So it hasn't actually had to write a minus sign in front of the 1. It's just done 0 minus a positive 1 to represent -1, which is just an interesting little aside. So I was feeling very pleased with myself. I thought, wow, that was way easier than I thought. I wonder how this can be broken. I can't wait to find out. And because I was so anxious to find out how it could be broken, I thought, you know what, I'm going to go on Elixir General and I'm going to announce a $100 US bounty for the first person that can make that test pass. And so I put that up soon. I think it was pretty much around Boxing Day, and I think I woke up the next morning and there we go. First exploit from this chap. Handle Voltone, but actually Bram. Sorry. Sorry, who is actually here on the meeting, and I apologise for giving you such late notice for that you're on, but it's really cool to have you here, and please pull me up if I misrepresent anything that you did or said in this rest of the presentation. So this one was basically it was gently pointed out to me that abstract code has nothing to do with the real code. It's only used for debug and some other tools like I think Xref and things, which is an Erlang thing. And so the thing that he was able to do was basically he could write his own version of what he wanted to do, and then just go and stick the same abstract code into his Beam file, and as far as I was aware, the file hadn't changed, but it was doing something completely different. So that was the first lesson, abstract code, and so that was so that meant I had to sort of like, okay, that was too easy. I can't just use the abstract code. I'm going to have to actually look at the real code. But if you ask Beamlib chunks for the actual code rather than the abstract code, it just gives you a great big block of binary, which is a lot less clear to decode or decompile. We do not get binary to term help this time. We're going to have to work on this, decompile this ourselves. So let's talk about how to decompile this code. And don't worry, I don't go. There is some skimming involved in this bit. So to start off with, the code chunk starts off with a header, which has some sort of useful information about the code. Now, remember, this is bytecode, and so if you haven't seen If you didn't see the last presentation, this is not like Erlang or Elixir code. This is much more like assembly language code. So you'll have things like, you'll have opcodes like move, move the value 0, the literal 0 value into the X1 register, and then move this into that register, or swap these two registers and then go and invoke this other function. So it's a lot more like if you've ever seen assembly code, then that's the sort of code that we're talking about here. Labels are like targets for go-tos when you're jumping around in that code. Yeah, it's got things like number of functions, and after the header, it's actually got the actual code itself. The opcodes are what are the rest of the code. So we parse out the header. This is binary pattern matching. We're just basically, this is equals for people who are new to Elixir, equals does not mean assignment. Equals means match patterns, like in Prolog or in some other languages, and it's actually very awesome and powerful when you get used to it. So this is basically saying, here's a chunk of binary. All of these all of these variables are going to get set to the things that you find at this spot in the binary, and then we're going to call ourselves recursively. Here's all the remaining stuff that we're going to parse. Here's a list that we're going to accumulate all the results of what we're parsing in, and here's the first item in our list, which is the information from the header that we've just pulled out. Okay. The next things that we need to do is we need to actually get through all the opcodes. So the first thing we do is we'll start from the bottom and work back up the top. The first thing we need to do is, like, there's going to be, here's some integer, 57 or whatever, and it's the next thing in the binary that you're looking at. So what does that mean? Well, there's a library in Erlang called Beam opcodes, and for whatever the current version is of this is code generated stuff. So every time that Ericsson release a new Erlang, Beam opcodes contains lookups that tell you what the particular integer means. So 57. That's actually going to be called, I don't know, it's actually 57, sorry, but it actually is a move command. It's a move opcode, and its arity is 2. It's going to have 2 arguments after it. Okay, so we can just look that up. So the Beam opcodes provides us that information. Yep. So yeah, and the sort of result might be move 2. Then we're going to have to delegate off to another function to actually parse out the arguments. And so in this case, it might be move the value 0 into the X1 register. Okay, registers are like spots where you keep variables or arguments to functions and things like that. You don't actually get to use named variables in assembly code. They're just little pigeonholes where you can keep things. And so we're going to have to do that. And then after we do that, we just continue parsing on the rest of the code after what we got to. And just keep chewing it all up. Okay. Oh yeah, and then we get to the end. All of the chunks are all aligned on 4-byte sizes, so there can sometimes be some trailing padding that we're supposed to ignore after the opcodes. So if there's less than 4 bytes remaining, then it's just going to be garbage on the end of the code chunk, and we should ignore it. And then, just like we were talking about how to stay order n in the Pascal's triangle examples, we built all of these opcodes. We parsed them in reverse. We built the list in reverse, and when we're doing our final, when we've reached close to the end or within 4 bytes of the end of our chunk, we're just going to return the reversed list of all of the things that we decoded. Now, parse compact terms. This is a deliberate gloss over because this is actually very hard. They did some stuff with in the Beam where they really wanted to be particularly compact with the way that arguments are represented. And I haven't fully implemented this. There are these tags to represent different values. So you've got a byte and you have to read particular bits out of it. And if you've got 000, it's a literal character. If it's 1, it's an integer. If it's 2, it's an atom. If it's 3, it's an X register value. And then I did most of these, but and labels, by the way, are like references of when you're going to jump to another spot in the code. A label is a numbered position in the code that you jump to. And there are some more complicated ones. Like, for instance, there are the lists are actually lists of values and jumping points, and they're used as dispatch tables when the code has to jump in, like a case statement. When you have a case statement, you've got to jump and do lots of different things. That's what the lists are used for. And this isn't fully documented, but the end result of that parse compact terms is it'll bring you back a list of what the arguments were for that opcode. So if we're moving the value 0 into the X1 register, you'd have arguments for move that looked like that. Yeah, you could do a whole presentation on tags and tag decoding, but there's lots of stuff about this in the Beam book. Okay, so that's the hardest bit. We'll then go to the easiest stuff about the other chunks. I remember we had some other chunks there. We had lists of literals and imports and exports and functions, and these are actually very easy to parse if you know the binary pattern matching stuff, it just makes this sort of code super easy and nice. So here, for example, atoms are just basically lists of strings. There's at the top of the atom chunk, there's a list of how many of them there are, and then each one has got a length of the string, sort of like a string in Pascal, if you ever did that. And then here's the actual. Here are some bytes of that length, and that's the name of the name of the atom, the next atom in the list. And so we can just quickly build up a list of here are all the atoms that are going to be used in this code. Because yeah, you'll find that with literals and atoms and things like that, the values don't appear in there with the opcodes. What happens is the opcodes refer to atom number 7 in the atom table, or literal number 5 in the literal table. That's how the code works. Okay, and that's the end of the decompiler and what it does. So where's my moving to the next one? Here we go. Okay, this is that's a sort of I'll just go back for a second. This is the sort of output that the decompile module that I've written that's part of Safish does. Here's a list of atoms, for example. There's all the different atoms that are being used in the code. So it's nice because you sort of like get these summaries of here's all the atoms you use. And this is actually the decompile of Bram's bounty 1 answer. So I thought it was just, guess was unchanged, but this is what he was actually doing. If we go down to label 9, which is where the guess function starts, you can see there's a lot more happening than returning -1 here. Here we can see a call to Erlang self to find out the PID of the current process and putting it in the X0 register. Here's getting the atom backtrace and moving it into the 1 register. So there's our 2 arguments. Now we're going to call Erlang process info. Dun, dun, dun. Or should we say bloody process info, because here's its first reappearance in here. And then what it's apparently looking, process info returns a tuple result. And we're going to pull out one of the second element in the tuple is a string, which has a sort of big stack trace of the process. And you can see he starts to do, he splits it on double carriage returns. And then after that, some other stuff starts happening. Start doing some string wrangling. So the interesting thing is, so we'll come to that in a moment. We'll come back to what Bram was doing. And then just down at the bottom here, I'm showing you this because these other tables are actually important, particularly the imports, literals, and opcodes are the ones that we're really interested in. Because imports, these are listing all the MFAs of the other module functionality of all the other things that are calling. So we can see Erlang process info has been called here. Split, find, there's a whole load of other stuff. Regex run is apparently being used. So that's a list of all the things that we're importing. And here we can see the opcodes that are actually being used. And we can call external function, call external function last position in the function. That's to do with stack management. Call external, anyway, so it's obviously not just returning -1. Okay, but keep in mind what the opcodes list looked like, the imports, and the literals, because those are going to come up in a little bit. I don't actually understand why sometimes strings appear in literals and other times strings appear in the string table. This time the strings are empty. That could just be this is a minimum viable decompiler to be able to solve the it is called Safeish, just to make the Safeish thing work. It could definitely have, there are lots of unfinished things in it. So let's look at this dastardly process info. If you call process info self backtrace, it will give you this string. And if you think of back to my test function, what happens is when we made that secret value, secret's just the name that we use up in Elixir. When we're down here in this stack trace, which is here's the test starting and it's calling Elixir EX unit runner and it's getting more and more calling function after function after function going up the page. When we get to, this is the function we're actually in, but if we look at the function that called us, we can see the Y register, Y1, actually contains the local variable secret. Okay, so that's actually just completely given it away. And so all, this is actually Bram's code. All Bram had to do was he called process info and got the backtrace string, split it up on double carriage returns, looked for the place where, looked for the right stack frame, which contains which is going to contain the Y register thing. Then he looks up this regex is just looking up the string with the Y register followed by a big number, and then he can just pass string to integer. And yeah, and very nice reference there, Bram, to 42 if he can't work it out. Yeah, so that's what he did. He compiled that, and then he went and just stuck my my previous simple bounties abstract code into that, and my old code was none the wiser. So I thought, okay, I've solved that. At least I'm actually decompiling. So hopefully I've solved that problem, and this is it's going to be we can sell this to the NSA. It's like awesomely super secure. I don't think that next one took very long. So what was happening this time was I knew about Erlang apply and Elixir apply. I knew about being able to apply using apply to call a function dynamically. And so I knew about the libraries, the Erlang and Elixir libraries that did that, but I forgot that there was actually an opcode for apply. And so all Bram had to do was call process info again with just using the opcode and not actually calling a function, an Elixir or Erlang function. So that meant that I had to start going through the opcodes. Working out that map set of opcodes and checking to see that wasn't an apply in there, for example. So I did that. And I think, how much time is this? 30, so another day later. So this is $300 US so far. The next one was, I simply had not, this is a 2-for-1. So this is Bram being nice to me, because he worked out a really easy one, which was that timer, the Erlang timer library seemed so innocuous that I didn't frankly check it very well when I was doing my review of all the different calls, and I forgot that there was apply after inside timer. So as Bram said, the first version he did of the response for exploit 3 was just to use timer apply after, but he thought that was he took pity on me at this point and said, okay, here's a more interesting one for you. Okay, so first thing learned is check the whitelists. I went back and did a whole pass over the whitelists again to really make sure that I'd, as best as I could, and I'm sure there are still some bad things in there, make a better set of whitelists. The second thing that he did was, you can write a function literal, like you can write ampersand function name /2 or whatever, to refer to some function. Now, you can just have that somewhere in your code, and it's possible to use an apply you can actually use an apply opcode and just refer directly to the literals table and call that function. So I think that's probably my best understanding of how that actually works. So that means you can't just look at the things that are actually called in the code section. Simply having a reference in the literals, a function literal, a reference to a reference to a function literal means that you can arrange your code so that you could put things into the right registers and call that function still to be called. And so that just meant that I had to actually check the literal table as well. And just in terms of like arranging this presentation, I sort of simplified things earlier because I showed you the final version of the decompiler. And so what happened was I was actually adding those opcode sections and the literal sections. I added them as I was finding out about these exploits. I went back and I improved the decompiler to add those extra tables. The minimum set of tables that I needed to be able to detect these things. Yeah, so it was a simple matter of like you go and look in the literal table and look, there's a reference to process info. So and so that was how that one worked. And I think by this time there was we had a little bit of a New Year's break while both of us probably went off to our New Year's parties and things like this. And this one came back, and this was just a bit embarrassing. I think this is the last exploit. So I had gone to all the trouble of building the unique list of opcodes, and then I completely forgot to check them. So that was a complete fail. That was just not being careful. And of course, there was another call to process info. Okay, and then so I fixed that, and now where we're currently sitting is bounty 5. Now, Bahram, be ready to stop me because I'm very carefully wording this one here. Bahram said bounty 5 is a step up in difficulty, but at the same time made me promise to never quote him saying it was actually safe. He did not say it was safe, and it is not safe. Okay, so that's definitely it is harder than it was, but then that's not saying much given some of the doofusy sort of learning mistakes that I was making. Now, I know that we haven't talked about how Safeish actually combines the decompiler output with the whitelists. So again, just as because I didn't want to show you, didn't have enough time to show you the evolution of this, but let's just look at the current version of Safeish, the Safeish code itself, and how it combines the decompiler output with the whitelists and the checklists. Okay, so first of all, we start having to, we call decompiler, and it gives us the all the nice information. And we're only interested in the imports, the literals, the opcodes, and the and so what we do is we okay. So first of all, yeah, just reminding myself here. Okay, so the first thing we need to do is build a list of the risks. Okay, so what sort of risks are there? There could be function calls, which we find in imports. There could be function literals in the literals table, and there could be opcodes like apply, or actually the sort of ones that are used for send and receive and other things that we don't want them to do. So we need to just build a list of here are all the risks in this bytecode. So all we do here is we take the literals and we filter out any using function info, because function info gives you gives you a nice breakdown of the module functionality stuff for a function literal that it's got. So we just build, so we can build up, if we find a function in the literals table, we just build up an MFA tuple and add that to our list of risks. Flat map is good because the result is a list. It allows you to sort of filter and map at the same time. So returning an empty list from a flat map function is the same as filtering out the element. And then the last thing we have is we have the imports, and we have to. So we take all of our imports, turn it into a list. We combine that list with the function literals that we just made a list of, and then we put them into the map set we have of opcodes. So now we're just going to have a list of MFA tuples combined with opcodes, which are just going to be atoms that are that this code uses. And it's pretty hard for this code to, I mean, I'm definitely not saying it's not possible, it probably is. But from what I know at this point, it would be very hard to do anything else other than call these functions or these, it would be hard. There's nowhere else to hide. Well, almost nowhere else to hide another opcode or another function, maybe, perhaps. Okay, yeah, sorry, I've actually forgot my little builds here, but yeah, imports or literals contain extension functions, external functions, flat map filters and maps the function literals, and we build a big list of risks. Okay, then the next thing we need to do is we need to look at every risk as it comes in, and we've just got like a multi-clause function here to look at each risk. And so first of all, if we get MFA, then if that MFA is we just do we look up all of our whitelists, so we can find out is the module whitelisted, or is it Erlang whitelisted, Elixir whitelisted, or is it an Erlang function or an Elixir function? If it maps any of those, then it's okay. If not, then we have to build an error message. So we we build up MFA, we build up a little error message that says this function, MFA, blah, blah, /2 is not whitelisted. So that's going to be our error message. Down here, we have the opcodes. And that's just going to be an atom rather than an MFA tuple. If it's a member of the whitelisted Beam opcodes, and most of them are whitelisted, there's only send and receive and apply, I think, are the main ones that are blacklisted, that aren't on the whitelist. We'll say okay. Otherwise, we'll say, hey, there's this opcode and you're not allowed to use it. And any other risk is acceptable. Now I look at that, I suddenly think, does that make sense? But I'm suddenly having a sudden great moment of doubt, wondering about whether that last line actually makes sense to be doing, or if it's a massive security flaw. But anyway, I'll just move on. That's the way the world works.
Bram will tell you for $100.
Yeah, exactly. I just started thinking. Yeah. Anyway, I'm confusing myself. Then now that means that's all the hard-coded whitelisted things have been covered here. But remember, we want to allow our users to be able to whitelist like an API module or something else that they want to be able to call. And so you'll notice that there's a second argument up here, which is just like an empty list. That is actually for the whitelist, the overriding whitelist provided by the user. And so what we do here is we just up above those previous risk acceptable clauses, we have versions where the list isn't empty, and we can basically, the user can actually put module function, module function, or MFA, or also some. Hey, was I behind? Oh yeah, sorry, I didn't press forward. I was starting to talk about this slide before. Okay, this is the block of risk acceptable stuff that's above the previous risk acceptable stuff. The second argument is the whitelist. You can either put a module function or MFA or whatever into the whitelist, and that will be added to the dynamically added to the whitelist for you when you load this module. Here because the internal opcodes for that are used for receiving and sending messages aren't as straightforward, I just made some aliases for receive and send, and they sort of go to what I think are the opcodes which are critical for that to work down in the bytecode. So receive is actually remove message, as far as I can tell in the bytecode. And then we're just going to kind of work through this. This way we can, before we get down to the ones with empty lists, we can chew through the list of user provided whitelist stuff just in these clauses. And then once that list is empty, it'll fall through into the previous risk acceptables that we were doing. And so at the top level, it becomes, we have things for loading bytecode and stuff, but I showed you previously, there was a fragment of code that just showed you I was using file read and loading some stuff. So all we do is in the check, which is eventually what's called by the functions exposed by Safeish, is we build our list of module risks from the bytecode. Then we just we map all the risks through risk acceptable to find out tick or no, or either say okay or give us an error list. Then we just use enum all to say if they're all okay, then we can say okay, here's your module, that module is fine. Otherwise, we're going to just basically aggregate all of the separate error messages into a single error message and say, error, this module, you can't, it's breaking these rules. You've got these unwhitelisted things. So that is how Safeish works with the decompiler and the list of whitelists. So the current state of the project is it's there. We're up to bounty number 5, and so $100 could be yours if you can work out how to get the secret number now that I've done that latest round of changes. And to Bahram's credit, I asked him for the payment details, and he didn't actually ever respond with that. So I asked him if instead I could actually donate the money to the guys who are writing the Beam book, which, as I said, is a great project. And he agreed. So I am currently doing a GitHub sponsorship of Happy Hacking, the authors of the Beam book, and I think that's through till April. So that'll be 4 months at $100. So so you don't necessarily have to take if you don't really need the $100. If you need the $100, I understand. I'm happy to pay that. But if not, I will put you get bounty 5. I can put that. I can sponsor Happy Hacking for an extra month. So so get out there, all you. We have to basically. Bahram needs to be. He's had a good run, but I mean somebody has to. We have to take the flag up and show that. We've got some other good Erlang hackers around the world, and maybe you can break this library for me. If you're thinking of actually using Safeish, and because you're going to write a universe simulation or something like that, then just a gentle reminder. It's called Safeish for a reason. It's because we're definitely not saying neither of us are saying that this thing is safe. I was so worried about that, I'd put it in the name of the whole project. The issue is important. If you run a Beam from an untrusted source, and really I'm very lucky that Bahram was the first person to respond to that, because it could have been some completely random person who decided to just go file delete my hard drive or something like that. So I am lucky that a white hat person was the first person to respond. But yeah, if you run a Beam file from an untrusted source on your own computer, you're playing with plutonium. Perhaps some scenarios under which you might use it with this in mind. If you were within a trusted group, like say we wanted to run a robot war tournament in the Elixir user group, and we knew who were contributing, but we just wanted to stop everyone's robots from hacking other people's robots, then then within a trusted group, you could use it. Maybe for next Elixir camp, when we go back into those days post-COVID. We could. This is why people, when stuff is closed source, you have code signing and accountability, and all the App Store type things. There is some sort of code signing in Beam, but it isn't really what. It didn't seem to really be what I was hoping for in terms of like Docker Notary or something like that. But yeah, you'd really need to have some sort of trust infrastructure set up to so people were accountable for the stuff that they wrote. And the other option is of course to run your Erlang VM inside a container with really limited resources. So have like a defense in depth, have a second sandbox around the sandbox, so that even if one does get out, there's very little it can do other than muck up the robot war tournament for everyone. So that's the conversation. I did manage it in less than an hour, so it's getting pretty late. Happy to take questions. And just another plug, the Beam book, I couldn't do any of this without the Beam book, because that's what tells me how Beam files work. Cheers.
Thank you very much, Robin. So does anyone have any questions? If so, feel free to mute yourself, turn on your screen.
I'll point out that Bahram is there to answer questions as well.
I want to hear his side of the story. Sounds like he had way too much fun.
Yes, well, let me just move my Zoom here so I can look you in the eyes. Yeah, no, I was actually not celebrating New Year. We don't really do the Gregorian calendar New Year in these parts. So I was actually having some quiet time when all my colleagues in other parts of the world were off on their Christmas and New Year's holidays. So I had too much time on my hands, actually. I was supposed to be working. Anyway, I do want to maybe add a few comments, if I may. So first of all, in one of the earlier diagrams that Robin showed, there was this line that showed what part of the code the sandbox would protect, and there was like a dotted line around the trusted functions that could then call untrusted functions. But so the assumption basically being that once I trust a function so much that I allow it to be called for my sandbox code, that function can in turn make hopefully safe calls into otherwise untrusted code and not do anything dangerous. That may be true in some cases. It's a very, I guess, that's really the main attack surface, really, and it also really depends whether you might be successful in exploiting any of those trusted functions to do untrusted things. Really depends on what is the bounty target. So in this case, the bounty target is a value on the stack, which there are only a handful of ways. Actually only really one or maybe two if you actually write Beam bytecode rather than writing Elixir code to get to these values. But if you're really sandboxing code, you have to protect against a lot of other types of attacks that someone might be able to pull off through this channel, through trusted code that then invokes untrusted functions. So yeah, what Robin said earlier is there are other approaches for sandboxing, such as Lua. Lua is really brilliant for this because you really define the interface that is exposed to the Lua program. The Lua program can't do anything without going through that binding that's provided by the Lua virtual machine. And the Lua language itself also has native capabilities for sandboxing. It's really designed specifically for this use case. So I wrote a document for the EEF, the Erlang Ecosystems Foundation Security Working Group, called the Secure Coding and Deployment Hardening Guidelines. I should probably copy a link in the chat. It has one area that it covers is exactly this, sandboxing, and it's basically saying don't try to sandbox the Beam itself. It's really not made for this particular use case. It's that there's like Robert and Joe have gone on record to saying security was not a design requirement at the time. They were designing for closed systems that were run in a private network. The fact that nowadays everyone puts the Beam on the internet, of course, has changed the equation dramatically, and it doesn't mean you can't run a Phoenix application on the internet. It's just you have to be careful what you allow the application to do, because once someone gets into your virtual machine, there's basically no way to contain them. And so it's been a fun project to look into what Robin did and trying to find creative ways of getting out of that sandbox. But like Robin said, I wouldn't endorse this as a secure sandbox for production use in a really in an environment with real adversaries.
Yeah.
Maybe one day there will be. There has been a proposal, and it was a very interesting proposal by someone who basically showed up out of nowhere on the Erlang mailing list, proposing a sort of sandboxing flag in the process at the process level. So each process, each PID in the Beam would get like a marker that says whether this process is trusted or not, and then anything potentially dangerous basically every function invocation, every attempt to send a message would be passed to a trusted function that would basically approve or deny that action. And that would have been a very interesting addition. It's just that, unfortunately, the way the Erlang OTP project is run by Ericsson basically means that they decide on the priorities, and they welcome open source contributions, but when it comes to making fundamental changes to the Beam like this, they have to weigh the question of like ongoing maintenance that they will have to do for their commercial customers against, like, they have to check if is this really worth it for them. Do they need it? Do their customers need it? And I guess that's why it wasn't picked up. But maybe one day something like that will be added to the Beam, and that would be very interesting.
That was actually another approach that I thought of, which is a lot harder, but would be to actually rewrite the code to try to basically, you appoint a sort of supervisor, some supervisor code, and then you rewrite the Beam so that basically every call that was going to be going to an external function or whatever actually goes to this thing first, and it gets to vet every call.
There actually is already something like that. I didn't want to mention it.
Okay, cool.
It might actually have saved you a lot of time. There is a module called erl-eval. It's in the Erlang standard library, and it's basically that you do just that. It basically, you can pass it some code and say, run this code, but call me for every function call you are going to make.
But is that actually bytecode, or is it more like?
No, so it's not running bytecode. It's basically running AST. So it's basically your first intuition of looking at the AST. That might still be a valid approach instead of relying on bytecode, because bytecode is so powerful, and it's really difficult to filter the bytecode. If you run the AST in a kind of interpreter environment and then intercept function calls at runtime rather than ahead of time, then you probably end up with more control, and you can plug a few more holes. Because again, there's the possibilities are almost endless for things to go wrong.
I think he said endless possibilities. Oh no, impossibilities. Sorry. Yeah.
Anyway, again, it's also very important to keep in mind that fetching a value from the stack is just one, like that was this particular exploit, but there's so many other things that you could do that could damage the system. Even like you said, I could have deleted files, and there may be other exploit channels, other completely new channels that I haven't explored yet, simply because they wouldn't help me for this particular case, but it might give me still capabilities that you wouldn't want someone that you don't trust to have on your Beam. Okay,
right.
That was my contribution. Anyway, it's been fun, so thank you.
Yeah, no, it was great fun. Thanks.